Okay.
And you can see the screen, sir.
Okay. Now let me repeat what I have mentioned in brief in the first class, and then I'll continue with the next one. Now previously we have derived the heat conduction equation for a rectangular Cartesian system for different possible situation, including the very general one where the conductivity is varying. In this case, the conductivity is varying and the heat conduction is taking place along all the three XYZ direction. There is internal heat generation and unsteady term. And then we have tried to show some of the simplified cases, like here we have a constant conductivity. When conductivity is constant, it comes out. Otherwise, it is again a three-dimensional unsteady heat conduction with internal heat generation. And for steady state, in the transient term, the time-dependent term will go out. So this is the equation for steady state. And if there is no heat generation, this is the equation for steady state, unsteady condition, three-dimensional steady condition. And for no internal heat generation and steady condition, this is the equation for unsteady condition. And then we discussed about I asked you to derive the corresponding heat conduction equation. Now, if you see this heat conduction equation, it is basically this second order equation in terms of XYZ, and it is also an initial value problem. So that it given a condition at the initial state, how it varies subsequent to that initial state, the temperature can be derived. So ultimately, if we derive this thing, this particular this equation or any equation, if we take, if we solve that equation, for example, this equation, if we solve, then we ultimately we can find out a functional dependence of t as a function of x, y, z and time, where x, y, z and time, they will be called as independent variable, and capital T, the temperature, is the dependent variable. Now, apart from x, y, z and time, it will also have certain other quantities. It involves certain other quantities that also can change from one problem to another problem. For example, in one problem, we may deal with copper as a material, so the conductivity for copper is to be taken, and the solution will be dependent on the value of conductivity of copper. Also, the corresponding value of thermal diffusivity will influence the solution. The value of G dot also will influence the solution. So, it is not that the solution for T will depend only on X, Y, Z and time, but also it will depend on the value of G dot and K and alpha. But there is a distinction between the nature of X, Y, Z and time and the nature of G dot, K and alpha. This capital T, the temperature, is dependent variable. We'll call X, Y, Z and time as the independent variable. Sorry, because the value of X, Y, Z and time, they can change independent of each other. That is, what will be the value of X does not depend on what will be the value of Y, what will be the value of Z, what will be the value of time. Similarly, the value of time does not depend on the values of X, Y, Z. So they are mutually independent of each other. And once we have a value of X, Y, Z time, then corresponding values of T can be obtained provided we know the value of G dot, K and alpha, where G dot is the volumetric heat generation term given in watt per meter cube, K is the thermal conductivity of the material, and alpha is the thermal diffusivity of the material. because the moment we change the material, the solution, the temperature distribution will change. So the temperature also depends on G dot K and alpha. But G dot K and alpha, they will change from one problem to another problem. If we change the material, if we have a different situation where there is a different value of heat generation magnitude. But for a particular problem, G dot K and alpha, they are fixed. They may change only if we change the problem from one substance to another substance, one situation having some value of G dot, another situation having some other value of G dot. But given a problem, the value of G dot K and alpha, they are fixed. So they are something distinct from XYZ. Even in a particular problem, XYZ and time, they will change from one point to another point, from one time to another time. But once the problem is fixed, G dot K and alpha, they will not change. So that is why XYZ and time, they are called independent variables, whereas G dot K and alpha, we can call them as parameter, which are fixed for this particular problem. But the parameter values, they can assume different values once we change the problem. So if we go to a different problem, their G dot may have a different value, K may have a different value, alpha may have a different value. So it is not that it is rigidly fixed. It will vary from problem to problem, but for a given problem, G dot K and alpha is fixed. So generally speaking, T will depend on G dot K and alpha just as it will depend on X, Y, Z and time, but G dot K and alpha, their nature is that it is fixed for a particular problem, it will not change for a particular problem. But X, Y, Z and time, they will, even in a given problem, X will range from some X equal to 0 to some L, Y will may vary from 0 to H, Z may vary from 0 to W, something like that. Time may vary from 0 to infinity, like that. So X, Y, Z and time, will call them as independent variable. G dot K and alpha, they will be called as parameters for this problem, and capital T is the dependent variable for this problem. Now if you look into this, the differential equation which represents the distribution of temperature for this particular problem, that distribution can be obtained if we can solve this differential equation. And if we look into the nature of this differential equation, we'll see that it is second order in terms of XYZ. And if we want to get a solution, then we must have a pair of boundary condition for x equal x for different at different values of x. We must have a pair of boundary condition at different values of y. We must have a pair of boundary condition at different values of z. And we must have an initial condition from where we can get the solution to subsequent times. So the initial time, if we know that thing, the temperature condition, from that point onward, we'll be able to find out the temperature for subsequent periods of time. Now, the initial time at which we should know what is the what was the condition, that time we can tell it as t is equal to 0, and we'll find
Yes,
out
sir.
the solution for temperature at time t greater than 0. That is subsequent instances of time. We'll find out the solution. Now, to solve this thing, we must have a pair of boundary condition against x, pair of boundary condition against y, pair of boundary conditions against z, and an initial condition at t is equal to 0. Now, there may be different types of boundary condition. That is what we'll discuss now. So, this will be the new thing for today. That,
Okay, sir.
that if you see, there can be different types of boundary conditions. One is called a Dirichlet type boundary condition, where the temperature value will be prescribed on some part of the boundary. Now, this is we can say this is a general body of a very pictorial, a generalized representation of a body in which we want to see how heat conduction is taking place vis-a-vis the surrounding. Maybe from the surrounding heat is coming, or maybe from the body the heat is going to the surrounding. Now, this body is bounded by some line that may be real, that may be imaginary, and that line we call it as the boundary of the body, and inside this you have the domain. Now, let me somewhat formalize what we can call it as a boundary and formalize what is known as a domain. What we'll be calling as a domain and what we'll be calling it as a boundary. The boundary, this consists of union of points. A boundary consists of union of points such that any point on the boundary will be surrounded partly by domain points and partly by non-domain points. If we take a boundary is a union of infinite number of points such that each of these infinite number of points, they are surrounded by some domain points and some non-domain points. That is, some points belonging to the domain and some points belonging to the surrounding. Whereas a domain will be called as a domain such that it is a union of innumerable number of points such that each of these points are surrounded by domain points only. If you take any point inside the domain, that will be surrounded by again points which are belonging to the domain only. But if we take a point on the boundary, that point partially will be surrounded by domain points and partially it will be surrounded by other than domain points, external points, surrounding points, like that. So that I'll call it as a definition of boundary and domain. And boundary will be now generally symbolized as capital gamma and domain will be symbolized by capital omega. Now the equation, the governing equation that we have derived, if you see, if you remember, that we have derived by taking a control volume inside the domain. The equation that we have derived, that is valid for points which are belonging to domain, and the domain means the points which are distinct from the boundary points. So that equation is not valid on the boundary. That equation, the governing equation, is valid only inside the domain or in the domain. And domain points and boundary points, they are mutually separate from each other. There is no point that is common to boundary and domain. Boundary is agglomeration of points that are only belonging to boundary. Domain is union of points or agglomeration of points that are belonging only to domain. They have nothing to do with boundary also. They are separate things. And the governing equation is valid only to the points that belong to the domain. It is not valid on the boundary. On the boundary, something distinct is valid. In fact, if you see a particular problem, you see the governing equation is the same for another problem also. The governing equation is something universal that is valid for all such similar class of problem. But the solution for this for a particular problem is distinct from the solution for a different problem. আমি একটু পরে ফোন করব। Now let us be once again, let us repeat that the governing equation is valid only for domain inside the domain, and that equation is very general for all such similar class of problem. But if you see, the solution for each problem changes. That is why they are separate problems. Now what is it that makes one problem distinct from another problem? It is the boundary condition that distinguishes one problem from another problem belonging to the similar class. So it is actually the condition of the boundary that makes a problem distinct, because all conduction problems, if you consider them, they can be solved by taking the most general governing equation, that is del x of within bracket k del t del x plus del y of within bracket k del, not k, kx, ky, kz, like that, and that kx, ky, kz in turn can be temperature dependent. Now, so one single equation the most general equation is valid for all problems coming under the umbrella of conduction heat transfer. But as we can understand, it it actually creates hundreds of distinct different problems. Now, what is the thing that makes the problem distinct and different from one problem to another problem? Although each of them may be classified under the category of heat conduction problem. Now, what I am saying is that is the boundary condition coupled with the initial condition that makes the problem different and unique. So, you can say the boundary condition and or the initial condition, we can call them as the condition of uniqueness. It is these are the conditions that make a problem unique. And one more thing that I'd like to add is that a full prescription of the governing equation and a full prescription of the requisite boundary and or initial condition. These two together makes a problem fully prescribed. Otherwise, if somebody specifies only the governing equation, it is an unspecified problem. Because so long as we don't know the boundary condition, we cannot solve the problem. Similarly, if we know only the boundary condition, we do not know what is the governing equation, we cannot solve the problem. So to solve a problem, to make a problem solvable, we must have the knowledge of the governing equation, the appropriate governing equation, and also the knowledge on the boundary, which we call it as the boundary condition. What was the initial condition, that knowledge also we must have to make the problem solvable. Now, I am saying we must know, apart from the governing equation, boundary condition and or initial condition. This and or I am telling because in some problem, if it is a steady state problem, then there is no question of any initial condition is not required. The problem is invariant with time. So in this class of problem under steady state, only boundary condition may be necessary to be known. Initial condition is a useless thing to describe over here. The solution doesn't depend on what was the initial. Whatever is the initial is the final, is also the condition at the in between time also, because it is time invariant problem if we are solving a steady state problem. But only for an unsteady state problem, we require to know also the initial condition. Now we'll also come across some problem where we may neglect the internal variation of temperature. We may come across certain problem where the temperature variation inside the domain is there, but that variation is negligible. We cannot deal with any heat conduction problem where there is no internal temperature variation. We cannot have a problem dealing with heat conduction regarding an isothermally heated body, because if it is a body under isothermal condition, that means there is no temperature gradient. That means there cannot be any heat flow. So a body under heat transfer means the body must have an internal temperature gradient. That means the body will have a temperature variation from one point to another point. But there may be certain problems where the internal temperature variation is not so high. So if the internal temperature variation is not so high, we can assume by applying our engineering judgment that yes, there is a variation, but that variation is negligible. So we can treat the whole body belonging to one particular temperature, but that temperature changes with time because the body is losing heat. So ultimately, the body will have a variation of temperature with time, but we did not to take the temperature variation with respect to XYZ. So there may be two different classes of problem. In one class of problem, under unsteady condition, the temperature may be a function of XYZ and time, and there may be another category of problem where also we are dealing with an unsteady state problem, but there temperature can be treated to vary only with time, but not significantly with XYZ. Temperature does not change significantly with XYZ, but it changes only with time. So we can simplify the problem as if temperature is only a function of time. Those class of problems, they will be called as a lumped parameter problem. where the temperature of the body as a whole can be treated as one single lump the body can be treated as a lump of isothermally heated body whose temperature is changing with time. Now these are the different variabilities that are possible, but whatever be the case, the boundary condition can be always classified under the category of either this one or this one or this one. What is this one? The first one. The first one, type of boundary condition. These are the three types of boundary condition we require to consider or we have to come across to make the problem solvable. One category of boundary condition, we will call it as a Dirichlet boundary condition, where the temperature must be known on some part of the boundary. For example, we have tried to show this part of the boundary having a boundary condition given by a known temperature. This boundary with suffix T is a symbol given to represent that on this part of the boundary we know how the temperature is varying with xyz, because different points on this boundary they may have different value of xyz, and the boundary condition itself may change with time. So the boundary condition also may be a function of time. But this is a very generalized case. In reality, there may be many problems where so much of generality may not be present. So there may be some part of the boundary where the temperature is prescribed, where the temperature is known with respect to xyz and with respect to time. This part of the boundary condition will be called as a Dirichlet type boundary condition, where the temperature is specified. There may be another type of boundary condition known as Neumann boundary condition or derivative type.
Sir, it would be specified as the boundary, na? Dirichlet's function. Dirichlet's boundary conditions, the temperature would be specified at the boundary, right?
We are talking about boundary condition.
Mm-hmm.
So we are talking of condition on the boundary. That means the condition on points on the boundary. Okay. So Dirichlet boundary conditions are where on some part of the boundary, if the temperatures are known, then it may be a fixed value, it may be functionally varying boundary condition. If the temperature is known, temperature distribution is known on the boundary, temperature variation is known on the boundary, then that boundary condition is called as a Dirichlet boundary condition or boundary condition with specified temperature. There may be another part of the boundary where temperature may not be known, but the gradient of temperature may be known. Then that boundary condition is called as Neumann type boundary condition. For example, here we have shown that the heat flux is known. Now heat flux is nothing but minus K into temperature gradient. Now del T del N means the temperature gradient along the normal to the surface, along the direction normal to the surface. So if we know the temperature gradient along a direction that is normal to the surface, if we know this thing, that means we know this thing. The heat flux also is known, because when we are talking of a problem which is to be solvable, we must know what is the conductivity of the body. So if we know the temperature gradient, that means we know the heat flux, or if we know the heat flux, that means we know the temperature gradient. So there will be a second category of problem where either the temperature gradient is known or the heat flux is known, which are synonymous basically. Now that type of boundary condition will be called as a Neumann type boundary condition, and that part of the boundary can be symbolized as gamma to indicate the boundary and q, small q, as a suffix to indicate that the heat flux is known. Now there may be another type of boundary condition where we neither know the temperature nor do we know the temperature gradient, but something else is known. There may be another class of boundary condition where we do not know either the temperature, so we do not know the Dirichlet type boundary condition, we do not know what is the temperature on that part of the body. Also, we do not know what is the temperature gradient on that part of the body. But what we know is that from this part of the body, the heat is being lost to the surrounding by maybe conduction or maybe radiation, and the conduction heat transfer coefficient is known as H, and the surrounding free stream temperature is known as T ambient or T infinity or T free stream. Now, if suppose if we have a body whose temperature is not very high, then we know that there will not be much radiative heat transfer, because for radiation to be appreciable, we must have a sufficiently high temperature of the body. So if you have a body whose temperature is not quite high, like its temperature is not of the order of maybe 1000, but maybe the temperature of the body may be a few, maybe part of 100, maybe 70, 80, 30, 40, something like that. So in that range of temperature, the magnitude of radiative heat transfer will not be significant, it will be negligible. But so long as the body is at a temperature higher than the surrounding temperature, if it is not insulated, we know that the body will lose heat from the inside to the outside surrounding medium. If the body inside temperature is more than the surrounding temperature, then just 1 minute. If the body temperature is more than the surrounding temperature, by surrounding temperature I mean this T ambient, and if the surface temperature is more than the T ambient, then we know that there will be heat loss from the body to the surrounding by convection. If the surface temperature and the inside temperature of the body is not very high, then only mode that will be significant is heat loss by convection. But if there is the temperature of the body is substantially higher, maybe 400, 500 or 1000 or beyond that temperature, then apart from the convection heat transfer, there will be also radiative heat transfer. Now, this term, the first term that we have shown, that indicates the convective heat flux given by H into delta T, where what is T? T is the temperature on the surface, and what is T ambient? What is T infinity? The temperature of the fluid medium that is far away from the body. The temperature of the fluid which is very close to the body, that may be substantially high, but if you move sufficiently away, then we'll see that the temperature is no more changing. That is called the free stream temperature. This T infinity, this indicates that free stream temperature, and this T indicates the surface temperature, which we do not know. Also, just if we think of the convective part, then we'll add the radiative part. Now, this is the convective heat flux, which is being lost from the surface of the body to the surrounding. And where from this heat comes? This heat comes from the inside of the body up to the surface. So the heat comes from the interior of the body up to the surface by means of conduction. So heat arrives at the surface of the body by means of conduction. And what is the conductive heat flux? That arrives at the surface from the interior of the body, the conductive heat flux is given by minus K into del T del N. So, and also we can tell that if the surface is a thin imaginary line which does not have any what you call mass, so what will happen is that whatever heat comes to the boundary from the interior of the body by conduction, that same heat will be leaving the surface of the body to the surrounding by convection. So we can equate the conductive heat flux to the convective heat flux. So this can be a boundary condition where this is valid by satisfying the law of energy conservation. This is the only thing that we can take advantage of. But what we do not know is the value of T, which is the surface temperature. Neither do we know the value of del T del N, which is the gradient at the surface, considering from inside to up to the surface. Is the temperature gradient measured from inside of the body up to the surface, is the temperature gradient measured on the surface, taken from the inside to the up to the surface. This gradient is neither known nor do we know this temperature. But we know that whatever be the gradient, that will be equated to the surface temperature through this coupling equation by virtue of the law of conservation of energy. That, and this will be valid if we consider that the radiative loss is not significant. But if the temperature of the body is significantly high, then we require to also consider the radiative heat loss per unit area given by sigma, the Stefan Boltzmann constant, the emissivity of the surface, that you probably know, or if you don't know, for the time being you accept this as some kind of a what you call surface property, and this T to the power 4 minus T ambient to the power 4. This is, I think, known to all of you, that the basic equation for radiative heat transport and the heat flux by radiation. So the heat coming from inside of the body by conduction must be equal to the heat loss from the body to the surrounding by convection, and the heat flux lost by radiation from the body surface up to the surrounding. And this must be satisfied because energy is something that is conserved. So whatever heat comes from inside of the body, that must be equal to the heat lost to the surrounding by convection mechanism and by radiation mechanism. So this is a boundary condition that involves a sense of known temperature and temperature gradient is neither specifying the temperature nor specifying the temperature gradient, but it is telling that the temperature gradient will be related to the temperature value through this equation. It is called a mixed type boundary condition, where both the temperature itself is involved as well as the temperature gradient is involved. That is why the name mixed type boundary condition. Now,
Okay, sir.
let me tell you one thing, that in Dirichlet condition, we know the temperature. Here we do not know the temperature. This is not known. Also, in Newman type boundary condition, we know the temperature gradient. Here, although this term is there, but we do not know what is the value of this temperature gradient on the boundary. But what we know is that whatever be the temperature gradient and whatever be the temperature on the surface, both are measured at the surface. The gradient measured at the surface and this is the temperature on the surface. So these two will be related through this equation. Neither this is known nor this is known, but it is known that these two will be related through this equation. If we can specify, and this is something that you can always tell if there is heat loss by radiation and convection. So this is a boundary condition that will specify when we cannot specify what is the temperature known on the boundary, it is not known on the boundary. And also, if the heat flux is not known and the temperature gradient is not known, then we can live with this type of a very general prescription of boundary condition, where we neither have an access to measure the temperature is not known, maybe temperature gradient also is not at all easy to know, but by some means we can specify the heat flux. But here, if neither is known, then this is a way to get out of this thing by specifying this mixed type boundary condition given by a temperature and the gradient, both given in a in situ sense together, but neither the individual values of temperature are known nor the value of the temperature gradient is known. Okay. Is it clear or any difficulty is there?
No, sir.
Now there may be some other part where somebody may say that this part of the body is insulated. Again, if you see, this insulation boundary condition is nothing but this type of boundary condition. Because when you are talking of the heat flux is known, insulation is also nothing but a known type of heat flux. That is, the heat flux is equal to 0. So if some part of the body, if we know that it is insulated, then it basically comes under the category of known heat flux or known temperature gradient. If some part of the body is, the boundary is insulated, then what is the gradient of temperature? It will be 0, because heat flux equal to 0, and that is equal to minus k into del T del N. So del T del N is equal to heat flux by minus k. So heat flux is 0, that means del T del N is also equal to 0. So these are synonymous, that if we specify a part of the boundary as insulated boundary, there it is nothing but a known heat flux equal to 0, or it is nothing but the temperature gradient is equal to 0. Okay. Normally, wherever we know the temperature, we specify that thing. Wherever we know the heat flux, we specify this thing. And if we do not know either of these two, we can specify this thing. If none of these are specified, then it implies that part of the boundary maybe is insulated. There is a way to understand this thing, that if nothing is specified, it implies that that part of the boundary is taken mathematically as a insulated boundary condition. Okay. So these are the boundary conditions that we must know, and subsequent to knowledge of this thing only,
স্যার
it will be possible to solve the problem. Hello.
স্যার স্যার বলছি ডেল টি ডেল এনটা তার মানে প্রত্যেকটা পার্টস অফ বাউন্ডারিতে কি পাল্টাবে তো? কোথাও ইনসুলেটেড আছে, কোথাও ইনসুলেটেড নেই নাকি?
প্রত্যেকটা পার্টে বদলাতে নাও পারে। ফর এক্সাম্পল, ধরো এখানটা ইনসুলেটেড আছে, তাহলে এখানটা হবে সবটাতেই হবে তোমার ডেলটি ডেল এন জি। আবার ধরো এটা হিট ফ্লাক্স জানা আছে, হেয়ার দ্য ডেলটি ডেল এন মে বি ইউনিফর্ম থ্রু আউট দিস length of the part of the boundary, or it may vary. Delta delta may vary because heat flux also may vary from point to point. So it may be a intern may be a function of xyz and time. This intern may be a function of xyz and time. That means this also may be a function of time on some part of the boundary. There may be another part of the boundary where locally it is constant. That is, it is not varying with xyz and time. That means in that part of the boundary, on that part of the boundary, the temperature gradient may be constant. It is invariant with xyz and time. Just as in this part of the boundary, we have shown that the temperature is known as a function of x, y, z and time. But it is not a compulsion that on this part of the boundary, temperature has to be different. On this part of the boundary, it may be specified that the temperature is equal to 100 degrees centigrade. So any point on this point of the boundary will have the same temperature 100 degrees centigrade, whatever be the coordinate of that point and whatever be the time that you are considering. So here, when you are describing the things, we describe the most general thing, that there may be some part of the boundary where the temperature may be specified, and the temperature may vary on that point of the boundary, on that part of the boundary from point to point, or it may change. Even at a point, the temperature may change with time, even though the point is fixed, so that the coordinate is fixed, but the temperature may change with time. But that is a very general thing. Most of the cases, when you specify a boundary condition, maybe in this part on this part of the boundary, maybe it is specified as a fixed value, say 5 degrees centigrade. Maybe here it is specified as 100 degrees centigrade. Suppose we have a body where some part of the boundary is heated to 100 degrees centigrade, and this part of the boundary is cooled to 5 degrees centigrade. Then what will happen? Heat will flow from this part of the boundary and ultimately come to this part of the boundary and go out. So the heat will flow from this part of the boundary to this part of the boundary, and it will not remain stationed there. It has to leave, because otherwise heat is coming, so it will go up. If it is a steady state problem, whatever heat is arriving, it has to go out. Even if it is not a steady state problem, whatever heat is arriving, there is no mass. So there is no possibility of accumulation of energy on a layer, imaginary layer of mass. So the heat arriving has to leave. Is it clear to you or not?
Yes, sir. Yes, sir. Yes.
Now, there is one more very important thing, small thing but very important, that I must tell before I proceed for the subsequent thing, is that for a problem to be fully eligible to be solved, for a problem to be fully eligible to be solved, we must have some part of the boundary where the temperature must be known. Suppose if you have a problem where on the entire part, or only what is known is the heat flux, temperature is not known anywhere on the boundary. If somebody specifies a problem where he knows the heat flux on some part of the boundary or all parts of the boundary, and there is no part of the boundary where Dirichlet boundary condition is available, that is, there is no part of the boundary where the temperature is known. If that type of a problem is specified, then that part of the problem cannot be solved. That is a ill-posed problem. That is called an ill-posed problem, or insufficiently known data is there, you cannot solve it. So for a problem to be solvable, we must have either a knowledge of this type of boundary condition or this type of boundary condition at least. But if there is a problem throughout for which if we know the heat flux and temperature gradient, that means that problem is ill-posed, we cannot solve that problem. So for a problem to be solvable, we must know Dirichlet type of boundary condition and or mixed type boundary condition, because mixed type boundary condition is also in a sense something where temperature is involved. So if in a problem this type of boundary condition is specified or this type of boundary condition is specified, then we can solve the problem. To make it specified, what we should know, what is the value of this H, the heat transfer coefficient, what is the value of the free steam temperature, and what is the value of the surface emissivity. If we know these things, then we can write this as a general form. And also we must know the conductivity of the body. We know these three parameters, is the conductivity of the body, the heat transfer coefficient H, and the emissivity of the body surface, then we can write this equation as a last ditch resort, as a last rescue point, because this is valid by virtue of law of conservation of energy. And what about this thing? The universal constant that is known to everybody who is knowledgeable. That this is Stefan Boltzmann constant given by a value of approximately 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. That is known. Whether somebody specified or not, it is known. So this is a universal constant. So we can write this. But if throughout the body somebody says that no, I don't know H value or emissivity value, or I do not know the temperature, only thing I know is the heat flux distribution over the surface or some part of the surface, then the problem will not be solvable. Why it will not be solvable? That I will demonstrate you by a simple problem when time comes. Is it clear?
Yes, sir.
So when a problem will be solvable, when Dirichlet and mixed type boundary condition is known, or when Dirichlet or mixed type boundary condition is known, that is the convective radiative type boundary condition is known, then we can solve the problem. But if we have a problem where we only know the heat flux type boundary condition or temperature type boundary, temperature gradient boundary condition, that problem can be solved. Okay. Now, having said this thing, we come to a case of a one-dimensional heat conduction problem. One-dimensional heat conduction problem under steady state. That is a problem where the temperature, the heat is flowing only along one direction. And when heat will flow only along one direction, when the temperature varies only along one direction. That means the heat is not flowing along the other direction, that is along y and z. That means T is not varying along y and z. Now, when we are telling that T is not varying along y and z, by that we mean T is not varying sufficiently along y and z. Even if it varies along y and z in a negligible sense in comparison to the magnitude of variation of T variation along x. Suppose if del T del x is much greater than del T del y and del T del z, we can say in an engineering sense that del T del y is equal to 0, del T del z is equal to 0. What do you mean something is equal to 0? When we say temperature gradient is equal to 0, means what? Means there is no temperature gradient. Means what? How do you know? By measuring the temperature at a series of points and taking the derivative of that temperature. Now, when you measure the temperature, there is always something, some error is there. We cannot tell definitely that the two temperatures which you have measured as 30 and 30, they are definitely 30 and 30. there must be some value after 30 point something that we cannot measure beyond a certain accuracy level of the instrument. So whenever we talk of measurement, there is always certain aspect of uncertainty of measurement. So when we measure something, we know that we cannot measure the value that is there. What we measure is an approximate value very close to that. So whenever we say something as 0, del t del y equal to 0, that means it is very near to 0. So when del t del y is equal to not necessarily equal to 0, but very near to 0, then also you can simplify this as equal to 0. Because our job is to make things simple so that the cost of solution is economic, cheap. Otherwise, our product will be extremely costly and people will shy away from us because they can have the same product elsewhere at a cheaper rate. So as an engineer, you must be always concerned about making something cheaper by making things simple, not unnecessarily, but out of necessity, that whatever simplicity the problem demands, we must include that simplicity. We must not make a problem unnecessarily complex. But in our zeal to make a problem simplified, we should not oversimplify the thing. We should simplify it only up to the extent that problem demands it. So the simplification will be done only to the realistic extent, but not by force. That whatever simplification is not valid, we should not simplify that part. We should make simplification that is only valid through our rationale, through our logic, through our justification, through our understanding. If we can simplify something, we must simplify it, because unnecessarily introducing complexity will lead to and the possibility of an erroneous solution. Also, even if it is not an erroneous solution, even if it is a correct solution, the cost of that solution may be unnecessarily high. You may have to hire somebody who is much more knowledgeable to solve that complex problem. His remuneration also will be high, so the cost of the product ultimately will become high. So we must simplify. Now, when we talk of a 1D heat conduction, a very common example can be the heat conduction across the thickness of the wall of a room. And as I have said at the very beginning of this class, suppose this is a cross-sectional view of the thickness of the wall of a room, where this L indicates the thickness of the wall. And the height of the wall, I have not shown that thing, what is the actual height, that may be quite large compared to the thickness. And the depth of the wall also, I have not shown, because that also is irrelevant to this problem, in the sense that this problem is a problem where temperature, we can show that temperature will vary only along this direction. Let us call this direction as equal to x, and we can call this as y, we can call this as z. So the height direction we can call it as y, the depth of the wall you can call it as z, and the thickness direction you can call it as x. And suppose we call this as equal to x equal to 0, and we call this face of the wall as x equal to L, where y varies from 0 to h and z varies from 0 to d, the depth of the wall. Now, on this wall, suppose there is a imposition of a boundary condition that the entire surface of this wall, left surface of the wall, varying from y is equal to 0 to h and z is equal to 0 to d, that entire surface of the wall, and x equal to 0. That part of the wall has a coordinate x equal to 0, y varying between 0 to h, and z varying between 0 to d. That entire wall is maintained isothermally at temperature T. Similarly, the opposite face of this wall, that is x equal to L and y is equal to 0 to h and z is equal to 0 to d, the other face of the wall, that entire face is maintained at a lower temperature T2, such that the relation between T1 and T2 is that T2 is less than T1. By some means, if we can maintain this thing, then what will happen? We can expect this being the hotter surface of the wall and this being a colder surface of the wall, the heat will tend to flow along the x direction, that is along the thickness direction, heat will tend to flow. And that it will flow, that means that there must be a temperature gradient along x, otherwise heat cannot flow in a direction where there is a zero temperature gradient. The heat will flow primarily along this. Why I am telling primarily is that if we take this point and this point of the on the wall, this point and a neighboring point on that part of the wall. Now, what is the temperature gradient at this point? That will be 0, because the temperature at this point and a neighborhood point both have the same temperature, because the entire surface is at the same temperature T1. So the temperature gradient at any point on this wall will be del T del Y equal to 0, and del T del Z also will be equal to 0, because of the same logic. So heat will not flow vertically along this wall, it will neither flow along Z. So there is no temperature gradient along del T del Y, there is no temperature gradient along del T del Z. So because del T del Y equal to 0 at all such Y, so del 2 T del Y square also will be equal to 0, because del T del Z is 0 at all such Z, so del 2T del Z square also will be equal to 0. And if we maintain a one face of the wall as T1 throughout, and the other face of the wall, if we maintain it at T2 throughout the length of time, then we should not expect any variation of temperature at any point inside. If it is maintained like that for hours together, then what we can expect is that whatever the temperature at some point inside this body, that temperature will remain invariant with time, because the surrounding condition is also not changing with time. So any interior point condition or temperature also will not change with time. So any point throughout this domain, the temperature will not vary along with time. So this is a problem where temperature is not varying with time. That is why this term also will be 0. And if there is internal heat generation, then what will be the equation? It will be d2t dx square plus g dot by k equal to 0. Because it is no more changing with y, t is not changing with y, t is not changing with z, t is not changing with time, it is only changing with x. T is only a function of x. So there is no question of a partial derivative. So the equation should be now recasted as d2t dx square plus g dot by k equal to 0. So that will be the simplified equation which is appropriate for this problem. And whenever you see this equation, when you become accustomed, you will understand that this is a problem that represents heat conduction only along x. It is a 1D heat conduction. Also, it represents heat conduction which is not changing with time. So it is a steady state heat conduction, steady state one-dimensional heat conduction problem. So when you see an equation like d2t dx square is equal to 0, this implies what it implies? It implies the mathematical description of 1D steady heat conduction without any internal heat generation. If it specifies d2t dx square plus g dot by k is equal to 0, what does it imply? It implies that it represents a conduction problem physically. It represents a problem physically that is happening, and the corresponding mathematical representation of that problem is that d2t dx square plus g dot by k equal to 0. What is the physical problem that it is portraying is there is one dimensional heat conduction along x, and the heat conduction is a steady state phenomenon that is happening over here. That is, it is not changing with time, but it is changing only with x, t is changing only with x, thereby heat is flowing only along x. And that rate of heat flow remains invariant with time. That is why it is a steady state heat conduction problem. Now, where this will be valid? This equation that we have written, we must, whenever we write this governing equation, we must also write the domain of applicability of that equation. That is, this equation is valid for such and such range of x. And there is no question of range of y for a problem that is 1D in nature. There is no question of range of z. That is why I have not shown the extent of y. It is valid throughout any y. It may extend to infinity, it may extend to wherever I don't know. So I am not showing the whole height and depth of this thing. But the thickness is finite. So this equation will be valid for x between 0 and L. This will be valid for x between 0 and L. By between I mean leaving outside the value of x equal to 0 and x equal to L. It is not valid at x equal to 0, is not valid at x equal to L. This equation is valid at x greater than 0 and less than L. So, the simplified governing equation will be d2 t dx square plus g dot by k is equal to 0 for x varying between 0 and L. X is greater than 0 and x is less than L. That will be the simplified boundary condition. Is the thing. The simplified boundary governing equation will be, we have to show the logic why it is happening that I have described. I'll give it to you. You can go through once again. It is very general, very basic, and it will become like a cakewalk for you in course of time. Nothing is there, but a lot of things are there to be discussed. The simplified governing equation will be d2 to dx square plus g dot by k is equal to 0 in, and this is valid in a domain that spans between 0 and L, not from 0 to L, leaving outside x equal to 0, leaving excluding the point x equal to L. It excludes the boundary, but it is valid inside the domain, in the domain. And the corresponding boundary conditions are t is equal to 0 at x equal to t equal to t1 at x equal to 0, t equal to t2 at x equal to L. Just wait for 1 minute. We require two boundary condition because this is a second order ordinary differential equation, a linear equation. I have missed one more point to discuss, linear and non-linear problem. That when time comes, I'll tell. I should have done it before. Now, this is a second order ordinary differential equation, linear equation, because there is no term like t into t or t into derivative of t. There is no higher order term for t. T, the highest power of t is equal to 1 here. So it is a linear equation. And if you see, to solve this problem, we don't require to know what is the thermal diffusivity. So it is a problem where we require to know what is the rate of internal heat generation and what is the thermal conductivity of the body. If you have two bodies having the same conductivity, having the same internal heat generation, but they have two different values of alpha, the thermal diffusivity, the solution will be the same. If you have two bodies having same thickness, having same boundary condition of T1 and T2, having same conductivity, having same value of G dot, but even if their thermal diffusivity varies, for this class of problem, the solution will be the same, because this, as you can see, the problem specification does not require to specify alpha value. It is independent of alpha. So when you solve a steady state problem, alpha is immaterial. The thermal diffusivity property is immaterial. It is independent of the thermal diffusivity. Thermal diffusivity property comes into picture only when we are solving an unsteady problem which involves a term like temperature derivative with time. And as we can see, temperature derivative with time, that involves a factor alpha, 1 by alpha. So long as this becomes 0, the whole term goes out irrespective of the value of alpha. Yes, please.
Excuse
Hello.
me, sir.
Ah.
Sir, can you, sir, we are having a numerical analysis class, or can you end the class as soon as possible?
Yeah, I thought it is actually 5 minutes from 11, but I'm just making a error of judgment. I thought it is 10:55. It is actually 5 minutes past 11.
Yes, sir. Yes.
So let me stop.
Yes, sir.
And
Thank you.
what you can do, each of you can write your roll number in the chat box and leave. Okay,
Okay, sir. Okay, sir. Thank you, sir.
thank you very much.
স্যার তাহলে আমি লিক করছি, ঠিক আছে?